Hello, hello. Hi, everyone. My name is Darko Pracic. I'm the Environment Art Lead at Embark Studios. This presentation is about how we create landscapes at Embark for UE5 using Houdini. Embark Studios was founded in 2018 with the explicit intent of revolutionizing how both games are created and how they are experienced by players. At this point in time, we are 4 years old and we've already grown to 290 people. We're a studio that is filled with curious developers who dare take big risks, and we all strive for real breakthroughs when it comes to automation and proceduralism, where we've made huge progress already. Let's go through the agenda for this presentation. We've already had the introduction. Next, we'll go into the background of this talk. I'll talk about our general needs as a studio, what the current landscape tools and workflows look like, and list our implemented improvements for enabling any artist to create realistic landscapes with ease. Then we go in depth. The first part is about how we treat and work with LiDAR and real-world data. And the second part will be about our everyday tools in Houdini that artists use when they work on landscapes. And lastly, a short conclusion. So going into the background section of this presentation, we need to see what our needs are as a studio and what steps we should take to get to a position where anyone can create landscapes. More specifically, anyone can create realistic landscapes. First, we're making free-to-play games as a service. This means that we want to give our players frequent content drops and expand and deepen our game over time. We should be able to reshape several square kilometers in a short time span. Second, our studio aims for realistic, high-end visuals. We love pushing quality to the next level, and that will, of course, influence production time. Our landscape workflows have to encompass everything from grand vistas in our craters to smaller parks in the finals. And any artist should be able to use those tools effectively and efficiently. Then we want to stay small. Our projects will max out at around 100 to 120 people. Each individual should be a T-shaped developer. In other larger studios, you'll have a specific team for landscape creation and one for vegetation and yet another for architecture. At Embark, each artist must be able to contribute in several of these fields. And lastly, iteration times need to be as fast as possible. Our projects evolve and expand quickly. Whichever workflow we choose, it should easily abide to design or art direction changes and deliver updates post-haste. How have we been making landscapes previously? Let's take a look at a few of the traditional tools and workflows. First, we have the landscape-specific DCC tools. They give artists a fair amount of power, but are difficult to work with. The next point seems minor, but matters from a UX point of view. Previous landscape workflows would involve processes and filters on a two-dimensional height field. We believe that transforming and shaping landscapes is more intuitive when done in a 3D context, with gizmos and handles that artists are used to from other 3D applications. And then I'll talk about why LiDAR and real-world data are key to fast production when it comes to realistic landscapes and why it currently isn't as fast as it should be for high-end games. The biggest factor is the steep learning curve for highly technical geospatial applications, which are often required when processing high-resolution LiDAR and imagery. Let's go into some details when it comes to current landscape DCC tools. Our landscape artists have been using the traditional landscape tools for years, and they are great in plenty aspects. They are powerful in what they do. They're often very well optimized, and in some cases, you can even see real-time results while adjusting a slider, which is great. You're often working with large landscapes, which of course is a lot of data, and being able to process that quickly allows you to iterate more. Another nice aspect is their erosion models. If you do become a master at the tool and you're an artist with a good sense for what looks realistic, then you can achieve satisfactory results. Yet another nice thing about some of the applications like World Creator and Instant Terra Also, they also have Unreal Engine plugins that allow you to send data directly into Unreal. But let's talk about why we feel that we want to move away from those traditional methods. So landscape tools come with a few problems. Attempts to recreate reality through generative methods are likely to fail. Adding a landscape DCC to our toolset will add yet another software that our artists have to master. We also don't want to invest in narrow software. And the lack of scriptability doesn't mesh well with our goals for automation. So, we strive for realism in our games at Embark, and historically it has proven to be difficult to achieve a realistic and believable result with traditional landscape tools. Here we have an example of a piece made with Gaea, and it is believable at a glance, but the artist had to probably understand a multitude of node parameters, filters, and erosion settings, and they would still be fighting an uphill battle trying to replicate something organic and natural. These tools get their output strictly from a mixture between pseudo-randomness like noises and simulations like erosion. Using only those methods, it's of course very difficult, or perhaps even impossible to fully capture what happens in reality, where landscapes are shaped by a myriad of factors over millions or even billions of years in highly intricate ways. One more reason for wanting to move away from utilizing traditional landscape tools is that we want to reduce the amount of software that our artists have to learn and master. Also, one of our passions is to release our tools and findings to the public, open sourced. And that becomes trickier when your process involves many licensed products. The third reason for using traditional landscape tools is that we'd like our applications to fill as many purposes as possible. Landscape tools are only built for one thing. At Embark, two of our main tools are Blender and Houdini, and those two applications combined provide a large content production platform. They're used by 3D artists, environment artists, VFX artists, character artists, and animators. Here's an example of why it's nice to have a landscape tool that can do other tasks as well. We wanted to try out a new look for our in-game map for our creators, and it was easy to send our gameplay location from Unreal to Houdini and combine it with the heightfield, and then utilize Houdini's rendering to generate a nicely rendered orthographic image with Karma XPU. After which, one of our concept artists could do their work and give it that old black and white satellite image look. And another production example, we could take the height field that we had in Houdini and convert it into a mesh with baked textures that is used in our front end. Being able to convert our entire landscape into a simple 3D prop complete with texture baking, all in the same application, is very valuable. And the final important reason for us to move away from landscape-specific DCCs is their lack of scriptability. They're difficult to make plugins for, and you can't easily place them in any pipeline or workflow without friction. Automation is very important for us. We want to automate any and every step that we can, since our artists should be allowed to focus their time on being creative and working on the things that matter to players. Next is the subject of struggles artists face when working with the two-dimensionality of traditional tools. Traditionally, when artists work on landscapes, they are working in a 2D context. And how they manipulate landscapes will often be by dragging sliders, inputting numbers, or adjusting something in a top-down 2D view. What we want to do is give the artists the same manipulation tools that they are used from other 3D applications. A move and a rotation gizmo for starters, and anything extra that we add should at least follow a common language that they're used to from Blender or Unreal. Like I mentioned previously, this might feel minor, but our artists were able to shape and reshape our game world in our creators in a much more intuitive manner, and do things that we previously had no idea on how to solve. As soon as we added tools to manipulate landscape assets as 3D objects, everything fell into place. And we could shape the world as we pleased. I will showcase later in this presentation how exactly we shape landscapes in this 3D way. So the probably most important aspect to previous workflows when it comes to achieving realism is LiDAR and other real-world data. LiDAR is a technology used to create high-resolution models of ground elevation. This technique has been absolutely essential for us when striving for realism, just in the same way that photogrammetry has been a standard practice for studios and artists that want to create realistic nature assets. When looking at nature asset creation, then photogrammetry is an obvious solution. You wouldn't sculpt the rock, would you? Both from the aspect of how hard it is to match reality, but also from the aspect of how long it would even take, even if you were the best sculptor of realistic rocks in the world. The exact same logic applies to landscapes. Trying to generate or sculpt realistic features is a no-go for us. If we look at this image, for instance, it's a section of a LiDAR dataset from the Grand Canyon. The terrain we see here is believable right out of the box because it is the real thing. Now, of course, looks aren't everything. We need to build landscapes that are traversable and technically feasible. But a sensible workflow would be to start with a real-world base. Then you do the large-scale level design to make landscape work for gameplay. And then when you have the rough gameplay edits ready, you can replace those features with matching real-world ones and get the best of both worlds. So let's look at what the LiDAR data actually is, and then we'll talk about one of the popular GIS applications that you'd use to work with the data. Let's see. If we look at this image, what you see are the points that the LiDAR system will gather into a point cloud representing the ranged surface. For geographical LiDAR, it's often gathered with an airborne system, where you have an airplane that has a laser camera in the bottom. That shoots a laser towards the ground, measuring how long it takes the laser to bounce back. Depending on the intervals, you'll get a dense or a sparse point cloud. And when we look for data sets online, we try to find those that are at least 1 point per meter. Here we see one of the products that you can derive from LiDAR, which is DEM, Digital Elevation Model. It's basically a grid of rows and columns that build up a surface. In this image, we can see an example of a Geographic Information System application, or GIS for short. In this case, it's an open source application called QGIS, which we still use in some rare cases. But I've recently put some time into automating away those steps as well by simple Python and command line scripts that we can run from Houdini directly. We don't want artists to have to learn this software, but the main benefits of it is that you can easily layer different data sets on top of each other, each having a different map projection model. So let's look at the required improvements, and here's a short list on what we have to cover if we want to reach our goals for realistic landscape creation. Processing LiDAR is quite cumbersome, slow, and requires a bunch of knowledge that you'll never need in any other aspect of game development. The GIF shows you how easy it is. Wait, I'm jumping. This should be fully automated. The only manual job the artist has to do is to find the data they want, and of course make sure that it's under a Creative Commons license and free to use. The GIF shows you how easy it is for someone to initiate a LiDAR conversion to usable assets. The artist clicks on one shelf button, picks the folder of the LiDAR dataset they want to process, and press OK. Then a PDG process will automatically spawn and start cooking, converting the files into usable heightfield assets. More on this soon. Then we need the tools and utilities that enable artists to adjust, mix, remix, and manipulate LiDAR-based heightfield assets in Houdini without compromising the quality. A couple of them would be the heightfield lattice HDA that we've made, which allows artists to transform their height fields with ease. We also need a way to procedurally generate believable colors. Previous workflows involved a lot of manual work trying to calibrate the colors on an 8-bit satellite image And removing buildings and low vegetation and shadows as well was a complete nightmare. So we need something that is generated. We also need ways of creating interesting masks for our landscape materials in Unreal Engine. Getting a wide range of masking and distortion features will be critical to make masks that don't pop out and look unnatural. And lastly, the export and import. Currently, we're not near where we'd like to be. We'd like to have a direct connection with Unreal, where we can send and receive data effortlessly through a plugin or a bridge. But what we have now is a simple export HDA, which can split everything into tiles, and you select the layers that you want to export, like the height layer or the color maps or the different material masks. So onto some actual Houdini tools. And our first main section will be about LiDAR processing and a first implementation of an asset browser. There are three main processes that we need to automate. We've only finished one of them, which is the one listed up top, and I'm currently working on the other two. The first one is where an artist has downloaded LAS or LAZ files and wants to have the data ready to use in a Houdini work file and in an easy manner. LAS or LAZ files are common file types that you'll get when you download LiDAR assets. So where we'd like to end up with our LiDAR assets is, so we want artists to be able to just drag and drop LiDAR height fields onto their landscape that they're working with. So we want to make the steps from LiDAR source to a usable asset in a library as automated and easy as possible. Gathering the data from sites online can be automated as well. Most sites provide you with FTP servers and lists where you can batch download everything with a script. The asset browser you see is just a photoshopped mockup. We haven't had time to build something like that. We have a simpler version, but this shouldn't be more than just writing a few PyQt file requests in ChatGPT, and it should finish the job. But I'm told you're not allowed to do that. But still, the main idea is for us to be able to grab a processed LiDAR asset and inject it into your work file, like so. So imagine you having a grabbed feature, and you can just put it into your landscape. And that's basically how it works today in our tools. Here we see the main PDG network that will read the LiDAR files. The first steps convert the LiDAR files into high-res, height-field files in BGO format. Then it will take those files and resample them to a much lower resolution and save those on disk. The reason for that is that we need a way for artists to quickly preview things. Loading in high-res height fields is slow. So we output the low-res files, and then further down in the PDG process, we import them, merge them, and output another height field that is composed of the entire dataset in a low-resolution format. Here's an example of what a complete dataset output in a reviewable resolution. And what I mean by reviewable is that you can navigate in the viewport. Usually you're working with a lot of data, and this I think is 16 million points, so you can rotate around and find the area that you want to use for your landscapes. The main node for this process in the beginning is the LiDAR import node, and I don't know when, but it has been updated a lot to allow you to select the different classification filters in your LiDAR points, like buildings, low vegetation, medium vegetation, and high vegetation. And that can be super useful for later when you want to create different material masks or mask away something that you don't like. Here we see the imported LiDAR points, and you transfer those into a height field using a volume from attrib.sop. This is the first iteration of a asset browser that I mentioned previously for our LiDAR content. You click a shelf button, and the list will be dynamically populated by the available assets on a network location. So that went a bit fast, but there was a shelf button click. So this whole preview mesh, I lied before, it's 56 million points, and we can still review it in real time. The entire Tenerife dataset is 2.5 billion points, and we want to being able to read the data by low-resolution proxies is crucial. I'm going to pause a bit. Let's see. Went by a bit fast. So let's see. Being able to read data by low-resolution proxies is crucial. We don't want artists to be stuck in 30-minute load times and applications crashing on GPU memory. You should always be able to work fast in a lower resolution mode and get the high resolution content in loadable chunks when needed. There are even volume compression possibilities to reduce the memory cost of your loaded data, but they should be used carefully since they may introduce artifacts. Let's see. So here's an example of a few of the classifications on the LiDAR dataset. We've transferred those as mask layers on each height field. And the ones we see here are buildings, low vegetation, medium vegetation, and high vegetation. That was a brief look into our LiDAR processing. Let's move on to our height field tools in Houdini. So we're using the Gaea bridge. It is a useful utility, and that's something that isn't anything we've created. The Gaea Tor processor that SideFX Labs has built, which acts as a bridge to in Houdini. I know I've talked about how we try to stay away from traditional landscape DCCs, but we still need a powerful erosion model from which we can get nice-looking deformation. And even more importantly, we need different masks like erosion flow and sediment deposits for our in-game landscapes as material masks. We will mostly rely on real-world data, but there will be cases when we need to fill the gaps with procedural solutions, and having a bridge to Gaea in Houdini fills that gap. For the masking part, we are using both standard Houdini height field masking nodes, which offer a great range of feature-based options. To supplement that, we also add some flow maps from Gaea. Using the erosion in Gaea with a very short duration in the simulation will give you these nice and thin flow lines. Two of our other favorite nodes are the distort by noise and distort by layer. Especially using the distort by layer node on masks with the height as a gradient will give you a directionality to the mask. Here's a short demonstration on how we utilize the Gaea bridge for cases where the artist had to manually shape out a piece of the landscape. So I'm just using the nodes where we've set up for masking and adjusting the landscape with a levels-ish node. And distorting it a bit with noise. And then we add the Gaea process, which applies erosion to the masked area. Like so. I mentioned that we need ways to generate colors. Let's take a look at our current solution. On this slide, we see a few results from our height field color nodes, which procedurally generates colors for our landscapes. Our main goals have been to produce both large-scale variations that feel natural, but also a high-frequency breakup, which is what the players will see in their near proximity. Here's an overview of the HDA. It relies on an input image that gets converted into a color ramp. This is made possible by an HDA made by James Robinson, and it's available on GitHub and Orbolt. After that, we generate a bunch of masks with Gaea, which will be used in several of our coloring categories or layers. We have a base layer, a slope layer, a plateau layer, and a flow layer. This is just the current state, but we feel that you can go infinitely deep with this and define a multitude of features for coloring. So we get the large-scale variations. The way to get the large-scale variation is to map a low-frequency noise or a large-scale occlusion mask onto the generated color ramp. In this case, I think the noise is set to a scale of 900 meters. To break that up, we map something that has a higher frequency of microgradients to a color ramp. And when we blend them together, we get these large variations with detailed breakup. So align and lattice. Onto a few of our tools that will fall into the work in 3D category that I mentioned earlier in the presentation, where I compared 2D tools versus 3D. I'm going to play a video that will probably be too fast again. First, we locate the area that we'd like to improve. We're looking at about a square kilometer of gameplay area here. We load some LiDAR data that we intend to use as a replacement for the height field in that area. And we crop out a specific section that we need and load the high-res version of it. So next, we crop out the section a bit. And then we align the LiDAR data with our in-game landscape using our height field align node. And we then make the shapes fit more neatly by using a lattice. This allows us full 3D control of the landscape. So at the end there, I'm toggling between the before and after, which shows us the improvement that we get. And here's what it looks in Unreal. That's a nice change. So on to Houdini engine. We're using Houdini engine in a few cases, and one of the HDAs that we have is the height field cliffs HDA, which takes the landscape in Unreal as input and then generates a mesh that gets displaced by a tiling texture. And then from that high-resolution displaced mesh, we create a low-resolution mesh, and then we just apply the material in Unreal on that. So let's look at the demo. This is a bit sped up. Trying to find a good sun angle is the main work here. Here's another example of that height field cliffs video. Yep, and we have another HDA that we use quite frequently. We're using world composition in Unreal, and we have a 64-tiled landscape. And at a certain streaming distance, those tiles will load in the level LOD instead. And in that LOD level, we just keep a static mesh that is a LOD. Essentially for the landscape. But that is generated with this HDA that also just takes the landscape as input. It makes a nice low poly model, and it bakes down the normal map. We've also rebuilt a simpler version of our entire landscape material with all the layers. So that gets applied in Houdini as well when you input the landscape into this HDA. So here we see the landscape tile. And you just cook the HDA. And you get a low resolution LOD. And just to say, Unreal has built-in features for this, but we felt that we wanted more detail and more tweaking. And it looks good at a distance. We rarely see any popping or any differences when you're playing in the game. So we're already at the conclusion. This was way faster than I thought. So we have some nice things in place today. It is much easier for artists to build landscapes with our current tools, but these are just the first steps of a bigger journey. We've gone from having work files that take 30 minutes to sync in Perforce and 30 minutes to open to being able to reshape several square kilometers with highly realistic data and have it in game within 30 minutes. We've also gone from a point where we would have to be satisfied with the base LiDAR data and try not to alter it because that could ruin the features, to a position where we can both alter it to our visual liking, but also adjust any area to gameplay requirements as well. And I'm gonna end this presentation with a video montage of the world we've created for our creators. Thank you. I just wanted to say that me and my brilliant colleague Erik Hallberg will be presenting tomorrow as well at Side Effects. And those who come will get a 6-month indie license. That's all. Thank you.